We're now going to do some examples of area for lesson A20. The first thing you have to do when you're given a function is you need to take the time to graph it. Hopefully some of these you can graph by hand, but certainly utilize your graphing calculator as needed. Y equals x squared plus 4 is a parabola that is 4 units up. So if I just make a little note at 4 here, then we look something like that. And we want to find the area of the curve between the x-axis and the curve from -2 to 1. So we're looking at wondering how big a piece of area that is. This could be an odd-shaped piece of land or a piece of metal that we need to charge the area for. So let's take a look at that. Remember, to find the area between the curve and the x-axis is we're going to integrate from -2 to 1, and we're going to integrate our function because that's going to give us our function values at all of these points. So that would be x squared plus 4 dx. And so now let's simply integrate this. And so the integral of x squared plus 4 is 1/3 x cubed plus 4x. We want to evaluate that from -2 to 1. So take a second, evaluate that, and let's see what you get. Okay, so we should have, when we plug in, we should have 1/3 plus 4 minus -2 cubed is -8, so -8/3, and 4 times -2 is -8 as well. And when you work that all out, you should get 15. Now I would encourage you to know that your calculator has an integral tool under math called finite integral, and it is very helpful as long as you understand what the calculator is doing. Remember, on the discussion of area, when the area is below the x-axis, the calculator will read that as a negative, which is okay sometimes and not all the time. So be aware of that. When you put this in the calculator, you put your function. You don't need to put your dx, but you do need to put your x here. This tells you what you're with respect to. And then you put your a to b. So in this case, I put in my calculator x squared plus 4 comma x, because that's with respect to x, -2 comma 1 on the finite integral, which is under math, and you should get 15. If you just use your calculator and are not aware of what your graph looks like, you may end up not answering the question correctly. So the calculator knows how to do the integral, but it's in relation to the x-axis. Let's take a look at the next example, y equals 2x and y equals x squared minus 3. Take a second and graph these. So first I'm going to graph y equals 2x, which is a line that goes through 0. And then y equals x squared minus 3 is a parabola that is 3 units down. And so it looks something like this. And we want to find the area from -2 to 1, but first we better pinpoint on where these lines are intersections so we know where -2 and 1 are. So I would encourage you could solve these simultaneously, or you could put these in your graphing calculator and find the points of intersection. So pause, if you will, and take a look at that. And if we do that, we find that the address of this point is at -1, -2, and the address of this point is at 3, 6. But we want to go from x is -2 all the way to x is 1. So we want to find the area of this piece as well as this piece. And because those two pieces have two different tops and bottoms, we're going to have to break this into pieces. So remember, to find the area between two curves, you do the integral of the top curve minus the bottom curve. But because this is crossing in between, we're going to have to break this into two pieces. So for the first piece, we can start at -2, but we're going to have to stop at x equals -1. So we're going from -2 to -1, and the top curve is x squared minus 3. The bottom curve is 2x. So that will take care of that little piece on the left. For the piece on the right, we're going to go from -1 to 1, and we're stopping at 1 just because that's what we were asked to do. We could go forever, but we're asked to go. So we're going to do the integral from -1 to 1. Our top curve now is 2x. Our bottom curve is x squared minus 3. Be very careful with that subtraction there. We're going to add these two integrals together because we want the total area of those two pieces. So we'll go from -2 to -1, and I'll just clean this up. X squared minus 2x minus 3. And then over here from -1 to 1, and I'm going to distribute that negative sign, so we get -x squared plus 2x plus 3 dx. And we need to integrate these separately because they have two different pieces of boundaries. So please pause your notes and figure out the definite integrals of those two and come back and check your answer. So once you've completed those definite integrals, you should have gotten that 7/3 was the area of the little piece and 16/3 was the area of the big piece, giving you a total of 23/3 for the area of that piece. And if we were talking about actual area, then we would use units squared. If we're talking about it representing something else like money, then the total value represented would be 7 and 2/3, or 7.67. Let's look at our next example. Our next example is y equals 5x, which again is a line that cuts through here. Oh, I went a little crooked. And 3x plus 10 is a line that starts up here at 10. Let's maybe make that 10. And has not as steep a slope, so it eventually is going to cross. And we want to go from 0 to 6. We know if we plug in 0 to each of these, we're going to be on the y-axis. If we happen to plug in 6 to both of these, 5 times 6 is 30. Over here we get 28. So this point is not 0, 6. So take a second and find that point of intersection. And this one is actually quicker to do by hand. If you set these two equations equal to 0, you get 2x equals 10 or x equals 5. So this actually crosses at 5 and 25. So if I want to go all the way to 6, then I'm interested in this piece here as well as this piece here. And so again, we have a two-piece integration. I'd encourage you to pause this and you try to write the integration on your own first and then come back. The integration then is going to have to go from 0 to 5, and the other one is going to have to go from 5 to 6. For the 0 to 5 one, remember that this was the 3x plus 10 graph. So 0 to 5, the top curve is 3x plus 10. The bottom curve is 5x. So it's top curve minus bottom curve. And then from 5 to 6, the top curve becomes 5x, and the bottom curve becomes the 3x plus 10. Be careful distributing that negative. So if I clean things up, I would get negative 2x plus 10 over here, and over here I would get 2x plus 10. And now you can pause and find the values of these definite integrals. Did notice we have one little error here. On that second integral, 5 to 6, we have 2x. This should be a minus 10 because we had to distribute that negative. So my caution to you all didn't work for myself. And so the integral of the first one from 0 to 5 gives me an area of 25 for that piece, an area of 1 for this piece over here. So this gives me a total value or total area of 26. One more example where we have two curves, and I would encourage you now to pause and try to set this problem up completely on your own before you finish watching the podcast or the pencast. And so the first step I hope you did was to graph the two equations. And so that's y equals x squared, and y equals x cubed. Going to be real careful how you draw this because you need to see how these things are going. You might even want to plot a point. 1, 1 is a point on the graph here, and for x squared, 0, 0 is 1, and let's do 2, 4. Okay, because when you do y equals x cubed, 0, 0 is a point. 1, 1 is a point, but 2, 8 is a point. So it gets very, very steep way up there. So at some point we're going to have to cross, and that is actually at the 1, 1. So your graph for x cubed comes below here, and I'm exaggerating a lot, but it kind of goes like that and then like that. Okay, so this piece right here is below. This piece is below the x squared, and then this piece goes inside of the x squared. So being very, very careful with your graphs. Now, I didn't really ask a question on this one, but let's just say we want the area of the curve bounded by the intersections, and so we just want this shaded area. So we would have to know that the points of intersection are 0 and 1, so we would go from 0 to 1. Our top curve in this case is the x squared, and the bottom curve is the x cubed. And so my point on this one is that you have to graph some of these and look very closely at the intersection. And so now if you do the definitive integral of that, you'll have the area of that small piece. And when you do, you should get the answer of 1/12. By the way, you can also calculate the integral when you're actually in the graph, but you have to be careful of what you're asking it to do. But just like for number 1, I encourage you to go back to number 1 up there and try the calculator. Calculate the integral by looking at the graph. So the key to being successful in looking at areas between curves is to graph them and to identify. I would like to jump back to number 2. And in number 2, the question on number 2 is, why did we not subtract on number 2? I'm sorry, why did we not subtract, or why did we not worry about the fact that the bottom was negative, that there were pieces below the x-axis? And the reason we didn't have to worry about that is we did top minus bottom. And the fact that the bottom in these cases were below the x-axis, that minus sign right there and the negative that you would have gotten for the fact that it would have been below the x-axis would have then added the two pieces together. So in a case where you're doing area between curves and part of it goes below, that subtraction will take care of that. In the event that you have a graph where you're doing the area above and then the area below, you do have to recognize here that your integral will be negative and that you would need to make that positive to add these two pieces together. So just keeping an eye on that.